Welcome. In this module, we'll dive deeper into the practical side of machine learning by exploring the mechanics of training and evaluating a model. We'll start with supervised learning and then move on to unsupervised learning. How a model learns to predict. The process for training a supervised machine learning model is an iterative cycle of 4 steps. Split the data. Divide your data into 2 sets, a training set for the model to learn from and a validation set for testing its performance. Train the model. Use an algorithm to teach the model to find patterns in the training data. Validate the model. Use the trained model to make predictions on the validation data, the data it has not seen before. Evaluate the results. Compare the model's predictions to the actual known answers. If the results are not accurate enough, you repeat the process by adjusting the algorithm or its settings until the performance is satisfactory. Let's look how this works for a supervised regression scenario. In a supervised regression scenario, the goal is to predict a numerical value. Once you've split your data, the model learns the relationship between the features and the label. A good way to visualize this is by plotting your data on a scatter plot and seeing the model fit a line through it. This line represents the model itself, which is then used to make predictions on new data. The next logical question is, how accurate is this prediction? This leads to the next step of the process, evaluating the model. You input the features X to generate a predicted value Y hat. By comparing this prediction to the known actual value Y, you can determine the model's accuracy. The difference between the predicted value and the actual value is called the error or residual. Commonly used metrics for evaluating supervised regression models include mean absolute error, MAE, is a metric used to evaluate the performance of a regression model. It measures the average absolute difference between the predicted values and the actual values, providing an easily interpretable measure of the model's prediction accuracy. Mean squared error, MSE, is a metric used to evaluate the performance of a regression model by measuring the average of the squared differences between predicted and actual values. It's particularly useful because it heavily penalizes large errors. RMSE measures the standard deviation of residuals, or the prediction errors. It's in the same units as the data, making it easy to interpret, and its squaring of errors means it disproportionately penalizes large mistakes. Coefficient of determination R² is a measure of how well a regression model fits the data. It represents the percentage of the dependent variable's variance that can be explained by the independent variables, with a value closer to 1 or 100% indicating a better fit. While these concepts can be complex, you only need to understand the principles for the AI-900 exam, not the underlying mathematics. In a real-world scenario, you don't just train a model once. Data scientists use an iterative process of training, evaluating, and refining the model. They may try different features, choosing which data columns to use, like number of bedrooms, location, etc. Different algorithms, switching from linear regression to another algorithm, adjusting parameters, tweaking the algorithm's settings to improve performance. This cycle is repeated until the model's evaluation metrics are good enough for the specific problem you're trying to solve. Now let's look at how this works with a binary classification model that predicts categories, not numbers. Instead of giving a simple yes or no, a classification model calculates the probability that a given input belongs to a certain class. This probability is a value between 0.0 and 1.0. For example, a model might predict that an email has a 0.9 probability of being spam, and a corresponding 0.1 probability of being not spam. Many algorithms can be used for binary classification, but a common one is logistic regression. Despite its name, it's used for classification, not regression. It works by deriving a sigmoid function, an S-shaped curve that maps any input value to a probability between 0.0 and 1.0. Just like with regression, you set aside a random portion of the data to validate a binary classification model after it has been trained. The model uses a threshold to turn the calculated probability into a final prediction of either 1 or 0. We can then check how accurate the model is by comparing these predicted labels to the actual labels. To begin evaluating a classification model, you first create a confusion matrix. This is a table that counts how many predictions were right and how many were wrong for each category. Correct predictions in a confusion matrix are located along the diagonal from the top left to the bottom right. When a model performs well, this diagonal trend is usually more shaded or highlighted. Accuracy measures the overall number of correct predictions made by a model. While it's great for balanced datasets, it can be misleading for imbalanced data, where a model might seem accurate just by guessing the most common outcome. For example, if you have 95 non-spam emails and 5 spam emails, a model that always guesses non-spam will have 95% accuracy, even though it never finds the spam. Recall, also known as sensitivity or the true positive rate, measures the model's ability to find all the relevant or positive cases within a dataset. It answers the question, of all the actual positive instances, how many did the model correctly identify? In our spam example, Recall tells you how many of the actual spam emails the model successfully found. Precision measures the accuracy of a model's positive predictions. It answers the question, of all the positive predictions the model made, how many were actually correct? Using the spam example, precision tells you out of all the emails the model said were spam, how many were actually spam. The F1 score is a metric that balances a model's precision and recall into a single value. It is particularly useful for evaluating models on imbalanced datasets, as it provides a more robust measure of performance than accuracy alone. Recall is also called the true positive rate, TPR. There's a related metric, the false positive rate, FPR, which is calculated as the number of false positives divided by the sum of false positives and true negatives. The true positive rate, TPR, and the false positive rate, FPR, are used to create a receiver operating characteristic, ROC curve, and the area under this curve, AUC, is the final metric. An ROC curve is a graph that evaluates a model's performance by showing the trade-off between its ability to correctly identify positive cases and its rate of false alarms. It helps to visualize how a model performs at different prediction thresholds. The area under the curve is a single number that summarizes this performance, with a higher score indicating a better model. Our next topic is multi-class classification. As we learned in the last module, multiclass classification is a supervised machine learning task where the model predicts which of several categories an item belongs to. Just like other supervised learning models, it goes through a process of training, validating, and evaluating to ensure its accuracy. Multiclass classification algorithms don't just assign a single label. They often calculate a probability score for each possible class. The model then uses these scores to predict the most likely category for a given piece of data. The two kinds of algorithm you can use to train a multi-class classification model are one versus rest, OVR algorithms, multinomial algorithms. One versus rest is a straightforward strategy for adapting a binary classification algorithm to a multi-class problem. Create a classifier for each class using each algorithm produces a sigmoid function. Multinomial algorithms. A multinomial classification algorithm is an alternative approach that predicts the probabilities of all possible classes at once. Instead of multiple simple classifiers, it uses a single complex function that outputs a vector, an array of scores. All the probabilities in the vector will add up to 1.0. The class with the highest probability is chosen as the final prediction. This is like a single model that says this is 70% likely to be an A, 20% likely to be a B, and 10% likely to be a C. A confusion matrix for a multi-class classifier works similarly to a binary one, but it's expanded to show the outcomes for multiple categories. To calculate the overall accuracy, recall, and precision metrics, you use the total of the TP, TN, FP, and FN metrics. Clustering. To recap, clustering is an unsupervised machine learning technique that groups similar data points into clusters. It works by finding patterns in unlabeled data on its own, without using any pre-existing labels to guide it. Several algorithms can be used for clustering, with k-means clustering being one of the most common. It consists of these steps. Your data's features are turned into coordinates that can be plotted on a graph. This process, called vectorization, converts the characteristics of each data point into a numerical vector. The number of dimensions in the vector corresponds to the number of features. You first decide on the number of clusters you want, which is called k. For example, to create 3 clusters, you set k to 3. The algorithm then places 3 random points on the graph. These points are called centroids, and they act as the initial center of each cluster. Every data point is grouped with the centroid closest to it. A cluster's center point, or centroid, is moved to the average location of all the data points assigned to it. Because this movement might make other data points now closer to a different centroid, they are reassigned. This process of moving the centroids and reassigning points repeats until the clusters are stable. Since there are no labels to check against, a clustering model's success is measured by how well separated its clusters are. Multiple metrics can be used for this evaluation, including average distance to cluster center, how close on average each point in the cluster is to the centroid of the cluster. Average distance to other center, how close on average each point in the cluster is to the centroid of all other clusters. Maximum distance to cluster center, the furthest distance between a point in the cluster and its centroid. Silhouette, a value between -1 and 1 that summarizes the ratio of distance between points in the same cluster and points in different clusters. The closer to 1, the better the cluster separation. To recap, supervised learning models are trained on labeled data and evaluated with metrics like MAE for regression and accuracy F1 for classification. Unsupervised models like clustering find patterns in unlabeled data, and their success is measured by how well separated their clusters are. Next, we'll explore deep learning and see how it builds on these fundamental concepts.